So this is the first session on signals and systems, and in this session you will get an introduction to signals. Signals is what we are going to talk about. So let us start. So we start by answering the question as to what is a signal. Now one simple definition of the signal is that it's any physical quantity that is a function of time or a function of space coordinates, that is called as a signal. Now we will clarify this by taking a few examples. Consider the room temperature. All of us know that early in the morning the room temperature will be low. As the sun rises, the temperature will increase, and as the sun sets, again the temperature will decrease. So temperature, room temperature is a function of time, is an example of a signal. If you consider the pressure wave that is emitted when a person speaks, if you consider pressure at any point in the space, that is going to be a function of time and corresponding to the audio signal. So that is an example of a signal. Another example of a signal is, suppose consider a picture. The picture consists of large number of pixels, and the brightness of each pixel depends on the coordinates, space coordinates. So that is an example of a signal. Although in this particular course we are not going to concentrate on space coordinates, that is actually a topic of image processing. So in signals and systems, most of the time we'll talk about signals which are functions of time. Okay. Now note that when we are talking about a signal, it could be a random signal which is either a noise or a signal which carries information, or it could be a deterministic signal like a sine wave, square wave, and so on. We'll say a little more about this later on, about random signals and deterministic, etc. But right now, in this introduction, this is good enough. All right. So as I said already, in this course, we are going to concentrate on signals as a function of time. So function of space coordinates, we are not going to talk about. All right, let us now take a look at the notation which is used to specify signals. So the basic equation is x is equal to some function of time. So this mathematical description denotes a signal. X is the instantaneous amplitude, t is the time, and f is a function. It depends on the kind of signal. If it's a random signal, this would generate random values for x. If it's a deterministic signal, then ft will be a definite mathematical equation, maybe a sine wave or a linear function of time, etc. Okay. So as I already said, x denotes the instantaneous amplitude of any physical quantity, and t denotes time. Now there are two variables here. One is the dependent variable x and the other is the independent variable t. There are two variables. Now as all of us know from algebra, that variables can be described in two ways. They can be either continuous or they can be discrete. So the amplitude itself can be a continuous variable. And just to refresh your memory, by continuous variable, what we mean is that even in a finite range, the number of possible values that the variable will take on will be infinity, number of possible values. So the difference between the successive values is infinitesimally small. Such a variable is a continuous variable. On the other hand, a discrete variable will have finite number of values in a finite range. For example, take the example of integers. So you can have 1, 2, 3, 4, 0, etc. But nothing between 1 and 2. So in a finite range, the number of possible values are going to be discrete. So that is a discrete variable. And since in the description of the signal, you have got two variables, x and t, you can imagine that by appropriate combinations, you can get four kinds of signals. That is, both x and t can be continuous, both of them can be discrete, and either one can be continuous and the other can be discrete. So there are four possible types of signals. We'll take a look at them. Another thing you should note is that in most of the textbooks, Instead of writing an equation like this, x equal to ft, this is of course a very clear equation in which it is clear which is the independent variable, which is the dependent variable, and what is the function. But in many books in signals and systems, you will find the notation xt is used in a more general way. So depending on the context, xt can denote the amplitude x or it can denote the function. So don't let this notation confuse you. If you understand the context properly, xt can be interpreted to mean either the amplitude or it can be interpreted to mean the function. Okay. Now, as we have said, there are two variables, so four kinds of signals. So let us look at the first one, which is called as an analog signal. And in the analog signal, both the variables x and t are continuous variables. So as I said, both x and t are continuous variables, continuous amplitude and continuous time. So in short, CACT, continuous amplitude, continuous time. Such a signal is called as an analog signal. Now, if you plot any analog signal as a function of time, it looks something like this. I have drawn some random signal here. On the x-axis, you are plotting t, and on the y-axis, you are plotting x. So in this case, t is a continuous variable. So you take any finite time slice, the number of possible values that t can take are infinity. So you may start with 0 seconds. Then suppose you have 1 second here. The smallest value can be very small, 0.001, 0.001 and so on, infinitesimally small. So we are assuming that t is a continuous variable here. And x is also assumed to be a continuous variable. So for example, if x is a voltage and is from, let's say, -4 to +4, in that case this is a finite range, but the number of possible values in this are going to be infinite. So when you plot an analog signal, x as a function of time, you get a smooth curve something like this. That is your analog signal. On the other hand, a digital signal, both the variables are discrete. That is, you have discrete amplitude and discrete time. That is in fact the definition of the digital signal. Analog signal, basically both the variables are continuous variables. For a digital signal, both the variables are discrete amplitude, discrete time. Now it's important to understand that most of the transducers that we use in electronic systems, they give analog signal. A lot of them give analog signal. For example, take microphone. Microphone will convert sound into an electric signal, but the output of the microphone is essentially an analog signal. Microphone output, this is one example. You can have a thermocouple. Thermocouple output is a voltage which depends on the temperature, and again this is an analog signal. So if you want to obtain a digital signal, then you often require a component which is called as an analog to digital converter. This will convert an analog signal into a digital signal. So in order to understand how analog signal is converted into a digital signal, let us first look at the various steps in analog to digital converters, and then we shall consider each step in some more detail. Alright, so what is the first thing that you have to do? The first operation that you have to do on the analog signal is called as sampling. We'll see what sampling is in a moment, but right now what we are saying is what it does. So when the analog signal is connected to a sampler, the output that you get is a continuous amplitude signal but a discrete time. So when sampling is done, the amplitude, the nature of the amplitude variable doesn't change, it remains continuous, but nature of the time variable changes, it becomes discrete time. So the first step will give you a signal which is continuous amplitude and discrete time. Then what you do, you perform a process called as quantization, and this quantization will convert continuous amplitude into discrete amplitude. So at this point the signal is discrete amplitude and discrete time. So this actually is the definition of the digital signal, discrete amplitude and discrete times. But as all of us know, it is much easier to implement the digital signals if they are coded into binary. That is why you got one final process which is called as encoding. So that the output of the quantizer that you get is encoded into a binary signal. So right now we are not trying to see how sampling is to be done, how quantization is to be done, etc. But what we are trying to study is what is happening when sampling is done, what is happening when quantization is done, what happens when encoding is done. That's what we are trying to see. So we'll now consider each of these three steps in slightly more detail. So let's look at the sampling, and we can explain this in a simple fashion by using a graph. So suppose you are plotting t versus x. Now to make the matters clear, I have plotted the analog signal as well as the digital signal combined into this plot. So if you look at this continuous waveform, this is the original analog signal. And when you are sampling, what you are doing, you are taking the samples at definite time. So at t equal to 0, for example, x is equal to 0 itself. Then at some other time, so this is t equal to 0. Then at a later time, which is called as a sampling time, sampling interval, at t equal to ts, what you do is you sample the value. So that is equal to this value, and that goes to the output. Understand, when you are doing sampling, none of the values which are lying between 0 and ts, they go to the output. They don't. Only this 0 is transmitted, then at t equal to ts, whatever is the value of this analog signal, that is sampled and sent. Then again, the next value is 2 times ts. That means the interval between the successive samples is equal to sampling time. So this is 0, ts minus 0, this ts, 2 ts minus ts, again this is ts. So that is ts. And so in between values are not sent to the output. So that is why you are converting time into a discrete time. Understand that the time as it exists in nature is a continuous variable. But for our purposes, we are discretizing it. So it is not that the time is not present during this. It is just that we are ignoring it. We take the value at t equal to 0, and then we take the value at t equal to ts, ignoring all intermediate values. That is what we mean by discrete time. Okay. Now the question is, what should be the sampling time? What should be ts? And the answer to that is the ts is adjusted such that the sampling frequency, which is reciprocal of ts, 1 by ts, that has to be greater than equal to 2 times the maximum frequency content of the signal. Again, we are not proving this in this introduction, we are just stating it. But let us try to interpret what this means. Now, what is this f max? Now, if you consider an analog signal, it could be a random signal coming from microphone, or it could be some other signal, but it can be split into many frequency components, and it will have some maximum frequency component. For example, a speech signal may have a maximum frequency component with something like 3.5 kilohertz, whereas the full sound signal will have a maximum frequency component which is 20 kilohertz. So you adjust ts such that fs, which is reciprocal of ts, is at least 2 times f max. That is what this means. This is required so that at the receiver you are able to extract the original signal back. So later on we'll have more to say about this, but right now understand that sampling frequency is expressed in samples per second, and clearly it is reciprocal of the sampling time. Okay. Next, let us study quantization. Now, what quantization does? It converts the continuous amplitude signal into a discrete amplitude signal. So in order to understand that, let us look at this graph. So this black line that you show is of course the original analog signal, continuous signal, and you take the samples at discrete times that we have already seen. But now what do you do? So for example, at t equal to ts, you take this. Now this value that goes to the output is only one of the finite possible values. Let me explain. Let's say this sine wave has a minimum amplitude of minus 4 volts and a maximum amplitude of 4 volts. So if you talk about the continuous amplitudes, you have got infinite amplitude values between -4 and +4. But when we perform quantization, what we do is we don't use infinite values to be sent to the output. We take certain finite number of values. For example, in this case, we have chosen 8 values. So one value is at -3.5, the other is at -2.5, -1.5, 0.5, minus zero point 0.5, plus 0.5. If you count this 1, 2, 3, 4, 5, 6, 7, and 8. So this entire range from -4 to +4 is actually split into 8 levels. So what is the meaning? What is the meaning of these 8 levels? So what the meaning is, suppose you are taking a sample, look at this sample for example, t equal to 2 ts. Now the actual value is this. But in this particular segment, whatever may be the value, it is always approximated to the midpoint. So if the value is here, it is still approximated by the midpoint, that is 3.5. The value is here, it is still approximated. So corresponding to each segment, any amplitude will be approximated to the midpoint. For example, look at this sample. So here the actual amplitude is this, but it is quantized to the midpoint here. So in this case, for simplicity, I have taken only 8 levels, but you can have 16, you can have 32, any integer power of 2. We are saying integer power of 2 because later on these levels are coded into binary values. As we know, all digital signal processing is done through binary. That is why we are talking about the number of quantization levels as integer powers of 2. So in this case, you have got 8 levels. So you will require a 3-bit word. So the lowest level 000, this is coded as, this is 001 and all the way up to 111. Okay. So this is what the quantization process does. Note that when you are doing this, there will be certain amount of error. For example, the actual amplitude is this, but you have approximated it to this. So you can have an error here. So if this entire thing is q, the positive error can be q by 2, the negative error can be minus q by 2. Okay, and imagine this quantization will go on decreasing if you increase the number of quantization levels. Okay, this is just an example in which we have used 8 quantization. All right, that is quantization. Then encoding. So encoder, what it does, it converts the quantized amplitudes to binary values. So this entire block is A to D converter. You give analog signal as an input to this, and output is number of binary outputs. In our previous example that we saw, we had 8 possible values because we had used only 8 quantization levels. So you can have 16 possible values. In that case, it will be 4-bit word and so on. Okay, so that is what the encoding does. Then just to complete our classification of various signals, we can also consider this discrete amplitude and continuous time. So in this case, on the time axis, the variable that you have got is a continuous variable. Time is continuous. But here you have got discrete amplitude. So it may be this amplitude, and this remains constant until the next sampling time. And the next sampling time, maybe the value jumps to some value. So this jumps to value, but now remains constant. So imagine a situation like this. You have a digital to analog converter here, which will convert these values. For example, we saw that our maximum value 111 was 3.5 volts. So if this 111, this will be 3.5 volts. If this is 011, it will be lower than this. So again, how D2A conversion is done is a different thing. That's a circuits problem. Maybe later on we'll study that. But right now all we are saying is that if you have a digital input to D2A converter, you will get an analog output, and every till the next sampling is taken here, this value is retained. So this remains constant. So this is an example of a discrete amplitude and continuous time. Okay. Now, in order to get an overall view of signal processing system or a digital signal processing system, let's look at this block diagram. Typically, it will be like this. You got some analog input here, maybe coming from the output of some transducer, maybe coming from a microphone or a thermocouple and so on. So you require a to D converter. Output of the A to D converter is a digital one, so it can go to a digital computer or a digital signal processor. And so processing is done by a program here, or maybe by hardware that is done here. And then output is a digital, and if you want to convert it back to analog, then you require D to A converter. So the overall procedure is like this. What the program here, what it will do, program or hardware, whatever it is, it will first of all send a start conversion pulse. So every A to D converter will usually require certain amount of time in order to convert a given analog amplitude into a digital one. So when it starts converting, when it gets a input pulse which is called as a start conversion pulse, so it will start converting. It will take a certain amount of time. So after that the conversion is complete, and what it will do is it will send end of conversion signal to the digital processor. And once processor detects this, it will actually read this. Understand, unless the conversion is complete, there is no point in reading this. So you read this because then you will not get a correct value. So you read this only after EOC is obtained. Then you process it by a program or a hardware, whatever you have here, and then give it to DAC, and you get the analog output. All right, these are the basic elements of a DSP system. Now let us look at the notation for a digital signal. There are some nuances here. Now in this case, time is discrete. So T you can write as N into TS, where N is an integer. So this which we write at xt, T now becomes a discrete variable, so we write it as NTS. So if you look at it graphically, note that this is our original analog signal. We already seen this. I'm just explaining this notation here. So T equal to NTS, so N equal to 0, T will be equal to 0, N equal to 1, T will be equal to TS, and so on. So these are the digital output will look like. Now, although this is a correct way of denoting a digital signal, note that very often digital signal is denoted simply by dropping TS. So I'll explain that to you. You may call it as a normalized variable N. So the discrete time variable is NTS, where N is an integer. But very often, in fact, when digital signal processing is discussed, the TS is dropped. And the reason for this is that as far as the algorithms are concerned, the algorithm themselves do not depend on the rate at which the samples were obtained. To give you an example, suppose you are trying to calculate the average of 6 numbers, then what you will do? You will take the sum of all these numbers and divide it by 6, and you will get the average of 6 numbers. Now notice that this particular algorithm of calculating the average value does not depend on the sampling rate at which the values were obtained. That is why you will find that all books on signals and systems will denote a digital signal simply by Xn. Alright, so let me just repeat this. Usually only N is used because processing algorithms do not need TS. For example, consider the calculation of running average just now. A running average of course means that you will drop the last value and the previous 6 value and take the new one, calculate a new average, and so on. Of course, for implementation you cannot ignore TS. Understand this, that there is a certain rate at which the input signal is sampled, and the calculation that you are doing must be fast enough so that it's complete before the next sample is obtained. So as far as the overall implementation is concerned, you cannot neglect TS. That is obvious. You must sample at the appropriate frequency. You must read at fast enough rate. You must do calculations fast enough. but the algorithm itself for doing the processing, that does not require TS. And that is the reason digital signals are simply denoted as xn, where n is an integer. Okay, so that is what is shown here. This is a simplified notation. This n, so this is the 0th sample, first sample, second, third, fourth, and so on. When n is equal to -1, this is the sample, and so on. You find that this does not match exactly this because of the quantization error. In most of the textbooks, you will find that people can consider signals which are continuous amplitude, continuous time, and they consider signals which are continuous amplitude, discrete time. This can be done when the quantization error is quite small. So for all practical purposes, theory can be developed for discrete, for the digital signals by considering that quantization error is small. Very often the books will devote a chapter for quantization errors, and possibly will take that in some session or the other. But for the moment, note that digital signal in general will be specified in this particular fashion. All right, so that gives you some introduction to signals, what signals are, how they are defined, what is their classification. Of course, this is not a complete story on signals. As we go along, we'll study more and more. In our next session, we shall see how to generate some of the deterministic signals through MATLAB simulation. But for now, that's all.